So today we'll talk about the section 7.5. We'll talk about the powers and the roots of complex numbers. In Math 140, we know how to find the square root of any real number, right? For example, we can first find the square root of -1. So this is equal to I. I, the imaginary unit, this is the square root of -1. I itself not equal to -1, right? It's just the square root of -1. And we also know how to find the square root of any other negative number. For example, the square root of -9, you can use the product rule for the radicals. When one radicand is positive, another one is negative. So you have this guy equal to square root of 9 times the square root of -1. And then you have the 3i. But in Math 140, we don't know. Actually, we didn't learn how to find the square root of a complex number. For example, the square root of I, right? So we don't know how to find the square root of an imaginary number. So in this section, we will try to find the roots of any complex number. So let's begin with a complex number in the trigonometric form. So z is equal to r times cosine theta plus I times sine theta. Now let's see what is the square of this z. Square of the z, this is equal to r times cosine theta plus I times sine theta, and then times r times cosine theta plus I times sine theta. So we first multiply these two positive numbers, we get r squared. And then for this one, by the product rule for the complex numbers in the trigonometric form, we know we just need to add the arguments, right? So we have the cosine theta plus theta, you have the 2 theta. And similarly for the imaginary part, you have the I times sine of 2 theta. Okay? Now let's look at the cube of the z. Z cubed. This is equal to the z squared times z. And then you have the r squared times cosine of 2 theta plus I times sine of 2 theta and times r times cosine theta plus I times sine theta. By the way, before some guys complains that I should write all those deduction in a vertical way, not in the horizontal way, but I can tell you, because I have to save the space, otherwise I will run off the one page in a very short time. So I have to write all the things horizontally. Now let's multiply this moduli. We have the r cubed, and then we add the arguments. So 2 theta plus theta, you have the cosine 3 theta and plus I times sine of the 3 theta. Okay. So now you can see the pattern. If we have the z to nth, then we would have the r to nth When n is equal to 2, you have the r squared. When n is equal to 3, you have the r cubed, right? So if you have the z to nth, then the modulus of this nth power of the z is equal to the nth power of the modulus of this original complex number. And then similarly, the argument, that should be the n times the argument of this original number, right? So we have the cosine of the n theta plus I times sine of n theta. And this result is called the de Moivre theorem. The Moivre theorem. So now we will use this de Moivre theorem, try to find the powers of some complex numbers. And let's go to the page 628, and let's look at the problem 16. So we'll try to find the fifth power of 2 times square root of 3 minus 2i. If you do not use the trigonometric form and the de Moivre theorem, you have to multiply them one by one. That will, consume a lot of time, right? But right now, we can first rewrite this complex number in the trigonometric form, and then we can use the de Moivre theorem. So first, for this complex number z, we know the real part a is equal to 2 times root of 3. The imaginary part e is equal to negative 2. So first, we can find the modulus. The modulus r is equal to square root of a squared plus b squared. And this is equal to square root of the sum of the square of 2 times root of 3 and the square of the negative 2. Now this guy, square of 2 equal to 4. Square of the root of 3 equal to 3. 3 times 4, you have the 12. So the first one is 12. And the square of negative 2, you got 4. So you get square root of 16, and this is equal to 4. So now we can find the argument. And before we see, argument of a complex number is not unique, right? You can find many, actually infinitely many arguments for a complex number. But we just need one. So sine theta, we know this is equal to b over r, and this is equal to negative 2 over 4. So you got negative 1/2. Then theta, we can take this theta as the arcsine of negative 1/2. And we know this is equal to negative pi over 6. So argument can take a negative angle. So now we may rewrite this z to fifth as the fifth power of this complex number in the trigonometric form. So first we get the modulus 4 times cosine theta. Theta is equal to negative pi over 6. And plus I times sine of negative pi over 6. And to the fifth power, right? So now we can use the de Moivre theorem. So we first get the fifth power of this modulus. So it's the 4 to 5th. And then you get n times the argument. So 5 times this negative pi over 6. So you have the negative 5 pi over 6. And you have the I times sine of the negative 5 pi over 6.